Okay, in this video, I'm going to go over several methods of calculating the binary dependent variable. So simply put, a binary dependent variable is different from an OLS, a standard OLS model, because a binary dependent variable has its output determined by a single 0 or 1, or a yes or no. And so, in contrast to a standard OLS model, a regression model, where we have the y variable described as a discrete or continuous variable, we in this regression function, the output is in form of a probability of something happening or something not happening, or something existing or not existing, or whatever it is. Right here we have three models that are the most common for the binary dependent variable, what we call the linear probability model, LPM for short, the Probit model, and then the logic model. So in a linear model for probability, we have, again, a similar regression function, but we have the output as a form of a probability. But nevertheless, we could still find a marginal effect with the partial derivative rule. If we use the partial derivative of the output in respect to an x variable, we'll get the marginal effect. So pretty much the same. What's not the same is the way the variance is calculated. Because we are analyzing a binary dependent variable, we have to write the formula of the variance in a Bernoulli random variable, which is given by here. The chance of something happening, which is a regression function, versus some chance of it not happening, which is just the 1 minus the probability of the regression function. Okay, so say we're given this specific function here where we have an 0.3, a 30% chance by default to pass an exam, even if we don't study at all. But each hour we study, the chance of passing an exam is increased by 10%. And so if a student studies 4 hours for this exam, then what is the chance of he or she passing it? So obviously we can just input the 4 into the hours. 0.3 plus 0.4 is 0.7. So our answer in this case would be 70%. Now remember that the way LPM, linear probability model, is calculated, it's a constant model. It's calculated linearly. And that's important to know because oftentimes when we're outputting the LPM in the software, the percentage can be given sometimes by less than 0% or by over 100. So for example, if a student studies 9 hours, then we have a mathematical probability of 120%, which doesn't make sense because a probability can't go over 100%. And so we kind of just interpret that as it being 100%. Graphically, we can kind of see here. Again, this is basically a 1 or a 0 here. So the more hours we study, the more likely we are to pass the exam. But obviously, that's not always the case. We might study for 5 hours or 6 hours, and we might not pass it. We might not study any hours, and we still have a 30% chance. So obviously there's not a clear cutoff. And so the reason why we use different models, one of the reasons why, is because realistically nothing is ever 100% in a regression function. And so the LPM is problematic when it comes to those assumptions that something can be 100%, which isn't realistic. And so that's where the Probit and logic model comes into play. So the Probit model utilizes a normal distribution, not necessarily a linear model, but a normal distribution to calculate its probability. So given the phi here, I believe that's what the Greek letter is called, probability of a specific interval given by this normal distribution function here. Not going to read it all, but this is the normal distribution formula. And so if we're measuring something, a probability of a value being under a certain value, like if we call this z and we're finding for a probability that will be under here, then this is how we would find an integral of it. And so obviously because it's utilizing the the normal distribution, the z part of the function, we can't just do what we did in the LPM and just input the number of x into the variable and then just calculate it. We can't do that because we have to look at the z table afterwards. The derivative, because we are finding the derivative of the whole function, we have to use the chain rule because the derivative of this whole function is the derivative of the whole regression function in a Probit model is given by the whole regression function times the beta 2 by the chain rule. Simply put, the derivative of the cumulative distribution function given right here is the PDF given by right here, this line, or not the line, but this curve. And this is the normal distribution, or I try to make it the best as possible. Obviously it doesn't look like it, but that's what we're assuming. All right, so if we have a dummy variable to the left of our data, of our function, which is what we've been doing, and we also have a dummy variable to the right because we also might have binary variables to determine another binary variable. So, what is the chance that given that it's the sampled individual is a male, what is the chance that he is tall rather than short? So kind of like that. And so if we're trying to find those type of problems, then it is given here, where we're subtracting the delta that is determined by the slope of the binary variable, and we're just subtracting that off with our normal distribution phi factored into both functions. And so the way we mathematically estimate our coefficients or parameters in this Probit model is the software will use what we call a maximum likelihood estimator. This is an example of what I wrote, but this isn't really an algebraic proof. Again, I didn't think the algebraic proofs were necessary because 99 times out of 10 we do this by software. So we just have to know that it's using properties of, it goes through several possibilities and several types of models of what the probability will be, but it will choose the probability that's most likely to happen. Not necessarily the highest probability, but the probability, if by chance it chooses the lowest probability, that means that lowest probability is most likely to happen compared to the other probability chances that it considered. I know that might not be the most clear, but that's kind of the best way I could translate that. And so compared to the linear probability model, we have kind of a logistic curve. And this is far more realistic because, no matter how many hours we study, we don't have an exact 100% chance of passing the exam. Now, I did give the intercept as 0.3, so I don't know how realistic this would be or how well that translates to the original problem, but we have a logistic curve. Notice how the slope in the middle is the highest. And so intuitively we can kind of think that as when we are in like the mean of our studied of the average individuals, then that's where our pass percentage fluctuates the most. So even a little hours studied less or more can highly impact our chance of passing the exam. All right, finally, I want to go over, before I go into the logit model, I want to go over the different ways of reporting the marginal effects. So this isn't only applicable to the Probit model or the probability regression functions, but this is where we learned it. So I'm just gonna, that's also where I'm just gonna teach it right now. So the marginal effect that means is probably the most confusing way of reporting it, the marginal effect. It's simply just calculating the change of y based on x. However, all the other variables that might be included within our data set must be constant. So if we're determining the chance of a car crash, given that we are driving 70 miles per hour, then every other variable, such as what time it is or what type of car we're driving, all of that must be constant. Or sorry, all of that must be at their mean. So the mean maybe when we're driving is probably like 5 p.m. or whatever. So the other variables must be at their mean. And we calculated at their mean because we want it to be constant or ceteris paribus. Okay, marginal effect at a representative value. This is a lot easier compared to the MEM. So instead of finding the average, we look at a specific value and calculate the marginal effect at there. So again, using the car crash example, I mentioned like 70 miles. So what is the chance? So the MEM would simply just measure what is the chance of a car crash, not what is the chance of a car crash when we're driving 70 miles, but just simply put what is the chance of a car crash given these other variables are constant. The marginal effect at a representative value would measure like what is the chance of a car crash given we're driving 60 miles per hour, 40 miles per hour, and then it will conclude that's kind of the mean. We're not going to say that's the average, but that's a useful statistic we might consider. If maybe if we don't have a lot of other information. Finally, the average marginal effect, pretty simple. It's kind of what you think of when you think of the average. We can kind of think it as measuring the coefficient for all of the representative values of what we did here, but we add all of that up and then we just divide it by n. So literally just the average of this MERV, the marginal effect at representative value. So when we're doing this, I'd say the most common way of reporting, the most useful way of reporting is the average marginal effect. We can also look at the histogram of the marginal effect, but that's kind of like a more visual representation. We're not going to report that as a specific way, but usually what we would do is we would kind of sample it off the representative value. And then in conclusion, we will look at the average marginal effect to look at just the general effect or the most reliable effect of X influencing the probability of something happening. Obviously, given that it's a Probit probability model, it can be used for like a regression model as well, but what we did was a probability model. So, okay. So notice how I didn't cover the logit model yet. So that's what I'm going to do in the next video. I guess I can also go over which of these models will be, how we can determine these are preferred. But let me quickly look at, okay, so, the multinomial model. So that's also what I'm going to go over. That's when the probability of something happening isn't binary, but it's given by categories. So what is the probability that, a person might choose blue as their favorite color instead of red, or blue as their favorite color over red, yellow, green, etc. Okay, so that's what I'm going to do in the next video.